First of all, thank you, Lieke, for the introduction. And when Lieke asked me to give this talk about pertussis, I was thinking about, okay, how can I choose a title that is a little bit maybe provocative, and what I've changed it a little bit, and I've put between brackets why, and the question I think is immune memory failing? And so this is a discussion that I want to have with you today, and also maybe think a little bit about like what we mean by that this is failing. Well, this is a disclosure slide. So I do work with industry on especially on the Periscope project, which is an IMI project, but this is not really something that I will discuss today anyway. So what is pertussis? So pertussis is a respiratory tract infection which is caused by Bordetella pertussis, at least in the majority of the cases. There are some other pathogens like Bordetella parapertussis, Bordetella holmesii, which may also cause pertussis, but the vast majority is caused by Bordetella pertussis. It's a persistent respiratory tract infection, and some people also call it like the 100-day cough in China. And it causes uncontrollable and violent coughing, as many of you will know. So the transmission occurs via the respiratory secretions, and the R0, so the basic reproductive rate of this pathogen, is like in the order of 10 to 17, which is incredibly high. So it's really up there with measles, and measles is one of the most infectious viruses that we know of. So every person with pertussis will likely infect 10 to 17 other people. So the reason that we're here talking about this today is obviously because it's also a vaccine preventable disease. So like pertussis as a vaccine was first introduced in the Dutch National Immunization Schedule in 1957, first as a whole cell vaccine, heat inactivated, adjuvanted with aluminum hydroxide, and then in 2001 was first like an acellular booster was introduced at the age of 4, and then later on in 2005 it was completely replaced with an acellular primary vaccine. Now in many other countries in the world, like this date, it changes. Like some countries have switched, like for example in the US they switched to an acellular pertussis vaccine in the 90s. And there are also a lot of countries that still use the whole cell vaccine, mostly in African countries and also in Southeast Asia. So what does the disease look like itself? So I'm showing you this graph, and this is work like from Fritz von Koenig. And so like they're basically the classical stages of pertussis are recognized into or distinguished into 3 different stages. After the incubation, you have the catarrhal phase. It's really atypical, so you have a common cold-like symptoms, nothing particular about it. But then when you get to the paroxysmal stage, that's very typical of pertussis, and you get lymphocytosis, you get the vomiting hoops. Most of the cases, not always, you get no fever, which is also quite unusual for a bacterial respiratory tract infection, also because it's not invasive. And then over a very, very long period of time, you reach the convalescent stage. Now, you're only really culture positive in the early stages. The PCR positivity, like you're a little bit longer, it takes you're PCR positive for a longer period, but then like seropositivity, that comes after that stage as well. What I want to say here is that this is really like what you see, like this is really the classical. Like these are the classical symptoms. This is not what you always see. If you look at adults who have been vaccinated and who do get pertussis, like you see similarities, but it's not always the same. They're now also like when I was at the pertussis conference in Buenos Aires, like talking about it with people from South Africa, and they also see actually bacterial pneumonia with Bordetella pertussis, but without the violent coughing. So it has like really a spectrum of clinical symptoms, which makes it also difficult to say, okay, well, what are we looking at for protection? Now, this is basically the reason that I guess I'm standing here today, is because this is a picture from the USA where they, like this is the reported pertussis cases since the 1920s until 2014. And you can see that we're very steady, and then it starts to decrease with the introduction of wholesale vaccination. But then in the 70s and in the 80s, you see like a resurgence of pertussis. And look at this, this is a log scale. So, so the wholesale pertussis vaccine was actually very effective. But the major issue with the wholesale vaccine is that it was very reactogenic. And at that time, a lot of people didn't appreciate the severity of pertussis infections anymore and started to worry a little bit more about the side effects. So that also, and also some publications about it, led to coverage reduction to about 65%. Now, this is not the case in all countries, but this was certainly the case in the USA and also in other countries. And then in the 80s and the 90s, there were large-scale efficacy trials where they compared the acellular pertussis vaccine, which consists of only a few antigens, with the wholesale vaccine. And based on non-inferiority, this vaccine was licensed and it was introduced in the USA. Now, the worry about this is that the trend is still increasing, right? So we still see an increase in pertussis cases. But like in a lot of cases, actually, the resurgence started before the switch to the acellular pertussis vaccines. What we also see is that the epidemiology is changing. So, like what you see here is the age distribution of the reported pertussis cases, and what you can see here is that there's also actually like an increase in people who are vaccinated. Now, in the US, you see that there are also a lot of unvaccinated people who get, or young infants who get the infection. In a lot of cases, this is the primary concern, is that because these are the children that will, like if they get pertussis, they will, well, not always, but they can develop severe pertussis and even die from it. What is important to say as well is that it's not as clear in all countries, because the resurgence that you see is not always universal. And like what you see here is this is a slide, and with the dotted line, that indicates the time when there was a switch from the wholesale vaccine to the acellular pertussis vaccine. And whereas for some countries it's quite clear is that there is an increase, it's not the case in all countries. That could also be because of differences in surveillance systems, which are not always as good, I think, in all countries. So one of the things that people have looked at is say, well, maybe we're just at the end of a very, very, very long honeymoon, right? So, and so when, this is a paper from Riolo, he's from the group of Aaron King and Pej Rouhani, and what they've looked at is they've looked at contact rates. So this might not be surprising, but people tend to interact with people of the same age, right? So, and this is the red line in the middle, and that's especially true for children between say between 1 and 10 years old. And there is some intergenerational interaction, and that's obviously is with the parents. But when you model this into a transmission model, and you look at the fraction of the population that is susceptible in the different age groups, you see, and this is actually caused by this dip in vaccination coverage. You see is that the fraction of susceptible does increase over time, right? So that does contribute to the resurgence of pertussis, very likely at least. But we don't think it explains everything, right? So, and in this talk, I wanna talk to you a little bit about one of these explanations. And so, what are the proposed explanations for this resurgence? Well, one of them is awareness. We're actually aware that pertussis is not just a disease of infants, and that it also happens in adults. Obviously, surveillance systems have changed over time, right? So whereas 20 years ago, most of the pertussis cases were really identified based on culture, I think that has really shifted quite significantly to PCR at this moment. And that does affect the notifications probably. Well, the end of the honeymoon I already discussed. So pathogen adaptation, this is definitely also a reason for concern. And Marjolein will talk some more about it. And then the last, that's vaccine failure. Right, so what is the evidence of this, of vaccine failure in this case? Well, there is some like quite compelling evidence is that the duration of protection is reduced with the acellular pertussis vaccine. Now, this is a study from Australia, and this study was done. And what they did is they followed a cohort of children right around the time when they switched from their whole cell vaccine to an acellular pertussis vaccine. Now, and then they followed the annual pertussis reporting rates, and they categorized these groups into, stratified them into whether they had received a pure, like acellular pertussis primary course, or a pure whole cell pertussis course, or a mixed course, but then when the first dose was a whole cell, or when the first dose was an acellular pertussis vaccine. And what you can see here is that when the first dose is an acellular pertussis vaccine, is the chances of getting pertussis, like over time, is significantly increased. And there have been several papers like after this, is that the duration of protection is waning. Now, this guy, well, not maybe this guy, but baboons have been very, very, very helpful, because up until I think about probably 5 years ago, we didn't have any animal model that could actually reproduce disease, right? So we would have animal models such as mice, which you can infect, but they don't develop symptoms, right? So, and this was the first animal model that can actually look at disease. Right, so what they did is they infected these baboons with and then either these were naive baboons who were vaccinated with an acellular pertussis vaccine or with a whole cell vaccine, and they also included a group that they had previously infected, and that were convalescent animals. And what you see here is the white blood cell count. Now, like many of the doctors here will know, is that when you look at white blood cell counts in blood with the pertussis infection, that they go up really, really strongly. So this is the leukocytosis that I was talking about. And that's also like very strongly linked to disease, right? So if you don't increase your white blood cell counts like that, means is that well, it's not just the only thing, but it indicates is that you don't get sick. And this is days after challenge. And what you can see really clearly here is that the only group that gets sick is the naive group, right? So acellular pertussis vaccines do protect against disease, right? So that's important because that's what we want them to do, right? So, but then if you look at the colonization, so this is like on the y-axis you see the bacterial loads in these animals after challenge, and you can see, so the blue line is the naive, these are the naive animals, and they clear the infection over time, right? About like probably just a little bit over a month. But then when you look at the black line, that's the whole cell vaccinated animals. So they become infected, they're not sick, and they clear the infection in about like 2 to 3 weeks. Then if you look at the acellular pertussis vaccinated animals, is they have a reduced bacterial load, but they don't clear the infection very efficiently. So they stay colonized, and they actually stay colonized for significantly longer than the animals that are naive. Now, the green line on the bottom, those are the convalescent animals. So these were the ones who were previously infected, and they can't detect any bacteria in those animals. When you look at these animals, you see is that there are also differences in the type of immune response that they induce. Right? So when you look at just at the cellular, at the T cell immunity, you see is that the convalescent animals induce a very strong Th17 and Th1 response, but really not much of a Th2 response, whereas the whole cell induces a Th17 and a bit of Th1, and the acellular pertussis is really like more skewed towards Th2. So when we look at at like pertussis, we're really not clear what we mean, because in a lot of cases we mean disease, but now we're not always talking about disease anymore, right? So this is like what you see when you look at the clinical epidemiology studies, and they're really looking at mechanisms of protection and looking at disease, and we know is that both vaccines can do that. But these are really the subclinical infections, right? And this is when we talk about this, then we talk about the effects on transmission, we talk about the effects on immunity, and then like we know is that some of this is induced by whole cell vaccination, but we really don't know if these mechanisms of protection are the same, and are we talking really about like, are these two different beasts, or are we talking about the same thing, and do we require the same kind of immunity, and is that even possible to induce the kind of immunity that induces both protection against disease as well as protection against colonization? So I thought I'd put on this slide and to summarize the differences between the different vaccines, right? So like when you talk about location of the immune response, obviously, well, these are administered by injections, so majority of the vaccine of the immunity is systemic, right? And that is obviously a very clear differences between like infection-induced immunity, which is more local, right, at the mucosa. Obviously, the number of antigens is really different because these are only like 3 to 5 antigens. These have like over 1,000, but they're like all the antigens that are expressed during like the production process. But then during an infection, you will have additional antigens. So the match between like what you see, what the immune system sees, like during infection, and when it encounters that infection, is the best here. Antibodies, obviously, we've talked a lot about, like in the past, about that the acellular pertussis vaccine induces a very strong antibody response. Well, it does, right? And I'll come back to that like in a moment. But the whole cell vaccine also induces antibodies, but like you get also IgA during an infection. The difference in the cellular response. And then we have protection differences, right? So we have protection against colonization, and we think that this is the best way to induce protection against infection. Obviously, this is not something we can use to induce protection because it's not a vaccine, but we can learn from it. And whereas protection against disease, they all protect against disease. It's mostly the duration of the protection that is different. Okay, so we've introduced this vaccine quite a long time ago, and I think there now is accumulating evidence is that this duration of protection is short. But to be honest, the protection against like the duration of protection after the primary course is not, well, it's not as good as the whole cell, but it's really after the repetitive acellular pertussis booster vaccinations that you see a reduction in the effectiveness. And this is a study which was recently published from Nicole Klein. And what they looked at the California outbreaks. And this is after the 6th dose of pertussis, acellular pertussis vaccination. And what they show is that even like after 2 years, like your Tdap vaccine effectiveness has reduced to like 57%, and after 3 years it's 25%. And more than 4 years, you only have 9% vaccine effectiveness after a booster vaccine. So the ability of booster vaccination to protect is really not as good as we would like it to. Now, if we look at that and we go a little bit further and we look at for example, just this is a study from Annemarie Buisman's group who have looked at the like antibody distribution, and this is unreadable, so I decided to summarize it a little bit. And what you can see here is like looking at the antibody response, and I've focused on the IgG4 response here. You can see is that like after the 4th dose, you see is that for the different antigens, you see 29, 90, 91%, 47% of the children have an IgG4 response against that antigen. Now, when you go to like a 5th dose, you see is that level is really increasing, right? So it's virtually like almost all children at that time have an IgG4 response. Now, and this is actually a very similar slide, but then you see the proportion of the total antibody response that is directed again, that is like of the IgG4 type. You can see is that it's steadily increasing, right? And why is this important? Well, I'll come to that. So what happens during like vaccination? So like what you start off with is an IgM. Right, so IgM, so like an immature B cell will have an IgM response, and that's here, right? And then after, like over the course of a vaccination response, you'll switch to different subtypes. And these can be IgG2, IgG1, IgG3, IgG4, it can also be IgA, can be IgE. But what happens is during this process is a piece of the DNA is excised, and it's removed, and it's gone. And then you end up with this. And you, for example, in this case, it's a switch from an IgM to an IgA. Now, why is that important? Well, it is important because like there is some evidence now that the order by which the immune system switches over the course of a vaccination response is not completely random, right? So like you start off with an IgM. So IgM are low affinity, but they're very good in neutralizing or actually is in binding to antigens because they're pentamers. So their low affinity is really because you have 5 of them. The total affinity is increased, and then you switch to IgG3 and IgG1 and IgG2 and IgG4, and this is actually the order at which these genes are on the genome. Now the reason why this is important is because these antibodies are very good in inducing an inflammatory response, very good in binding complement, very good in inducing phagocytosis, whereas IgG2 and especially IgG4 has a very, very strong affinity, so it binds very strongly to your antigen. It can neutralize, but it cannot induce complement binding. So the complement binding of these antibodies is absent. This is the kind of response that you need, like, to kill your bacteria. And this is probably what you want to have, like, in order to reduce colonization. But this is the kind of response that we're getting at the moment, and that would really work well, I think, against toxins and other secreted factors where you have, if you have high titers of IgG4 and they bind to your toxins and they neutralize them and they don't induce inflammation, that's exactly the kind of response that you want. But I think that this is the difficulty, is that we are trying to aim for a similar immune response that prevents colonization and a similar immune response that prevents disease. So what happens then during vaccination? So when you have a whole cell pertussis vaccine, you get an IgG1 response mostly against many antigens, Th1, Th17, relatively low affinity. And then, like what has happened obviously in the past is that in order to also protect these children, they get repeated acellular booster vaccinations, and that works well because you get a strong IgG1 response, but the cellular response still looks a lot like what has been induced by the primary vaccine, and you get pretty good protection. But when you get a acellular pertussis vaccine, you get also a very strong IgG1 response. You get Th2 responses for the T cell response. You get a little bit of Th1 actually, right? So it's not as if it's completely Th2 at that time, but this really is skewed really strongly towards an antibody type response and a Th2 type response, and the avidity of these antibodies is really, really strong. So this is actually excellent, like if you want to neutralize your toxins and prevent disease. The problem is that these antibodies are not very good in killing these bacteria. And I think that this is what we're seeing now, is that like these children are not doing so bad, but these children are probably at risk. So then we get to the main question, I guess, is say, okay, what can we do about it, right? So like we can think about adjuvants, boosters, new antigens, maternal immunization. I'm not going to talk about it, but Nicolene will talk about it. And then I think we have to really define our priorities and what are the different options, right? So I think the main reason why these vaccines were introduced in the first place is to protect newborns against severe disease. And I think that's what they are still doing, right? And I think like the risk is that like with these vaccine escape mutants is that their protective effect is reducing, but this is still, I think, is very important, right? So we talk about maternal immunization, and maybe it's an idea to move towards like a pertussis toxin alone vaccine, because that is what really prevents disease. And then there are alternative strategies, although I think at the moment, I think the maternal immunization is really working well. And then the second thing is that we want to prevent disease, but also reduce transmission, and that's really more important. And I think it's the same what Louis Bond said this morning, is like you want to have different kind of protection in these infants and in older age groups. And I think the only way to do that is to improve or replace the primary pertussis vaccine. And a lot of people are talking also about improving booster vaccines. But suffice to say is that the initial results really suggest that the potential beneficial effects of BCG in this population are very, very small, right? And I think like this is in a population also that has been primed with a whole cell vaccine. Now, what would happen if you do this in a population that has been primed with an acellular pertussis vaccine? I think it will be very difficult because these Th2 responses are quite fixed, right? And I think it's probably impossible for these individual antigens is to switch like to a new class when they have already switched to an IG4, because the genetic material is not there anymore, right? So they can't switch back. So I think that new adjuvants alone are not going to be sufficient. So also new antigens will be needed. And like when you do this in a population of older individuals, that means that you're not really talking about a booster vaccine anymore. You're talking about a primary vaccine. So that will also make it a little bit more complex. So I wanted to say is like I start off because I think this is important to say is like at the moment, this is really what we've got. And I think the acellular pertussis vaccines do still save infant lives, right? This is important to mention. I think also is the evidence for a rapid waning of the immune response itself is weak. I think there is not very good evidence that immune response is declining more rapidly than with the T-cell, with the whole cell data. But what we do see over time is that the protection is waning, and it's not necessarily the same thing. The other thing that I want to mention here is that protection against disease is not necessarily the same as protection against colonization, and that we should really revisit this strategy. Like what do we do with infants? What do we do with maternal immunization? And what do we do with like all of these other groups that require protection, right? And I think the important thing here is that we really need to clearly define correlates of protection against like disease and against colonization. And that is something that we are obviously currently working on with this Periscope project, which is, has started middle of this year. And well, we're hoping to get some more data in that in the future. So there are some people I think that need to be acknowledged here. So the data on the protectin-specific B-cell responses, that's from a strategic research grant from the RIVM. The BCG study was initiated together with Professor Mir Netea from internal medicine, and Bas Blok has been very important in that study. And from my own group, Alice and Mark have been helpful in this. All right, so I think that's it. And the question I think are later, right?
Yes.
Yes.